Thank you. Well, thank you for the invitation to kickstart this series. I could also see in the list of participants a lot of names from Durham. So I think Richard has done quite a good job at advertising this to that crowd. So since this is a deep dive, I thought I was not going to talk about, showing you simulation movies and showing how great everything is, or talking about the derivation of the method or things like this. I want to talk about the things I've been worrying most about is how do we make an efficient implementation of SPH for the cosmology and astrophysics application we care about, and why things are the way they are, and what makes it complicated, and what is the HPC challenge we are facing. So it's sort of more on the technical side, on a deep dive on that front. So to get started, I should mention that myself, I'm quite involved in this. I'm the lead developer of the SPH Code, which is used for a lot of cosmological simulations now, especially in Durham and also in Leiden. And so some of this will be inspired by the experience we had developing this piece of software. To give you an example, and it's going to be a shameless self-promotion here, as we are speaking now, we have our big flagship Flamingo. This is an acronym, Cosmological Simulation, running on the new system in Durham. It's because there was the sort of commissioning time of the new Dirac Cosmo 8 facility. And maybe the interesting bit for this talk is this has, almost 200 billion SPH particles. And so this is the kind of things we want to do. We want to do really big simulations. I should say the naive thing is because the universe is really big. More about this in a minute. And I should say, so as far as I know, this is the largest SPH simulation that was not done in one of the big US DOE machines. Right? So I think this is pretty big. This is what we aim for. And this is what this talk is about, is how do we get there in the first place. So just a few slides on context. Maybe one thing about cosmological simulation and astrophysics simulation. One thing which is different from many other fields of science is that in astronomy, we really don't have the ability to go to a lab and make an experiment and then test our theory against that. Right? You can't go to the lab, make a star, and test whether your theory of stars is correct. So the only thing you can really do is simulations. And so simulations have been at the core of theory for a long, long time. And here's a classic example from the early 80s, establishing essentially our cosmological model, where simulating different universes with different models for what the constituents of the universe are in terms of the model of cold dark matter or hot dark matter model. It doesn't matter if you don't know what they are. On the left, you have two different models, and you have the ones in blue or three different models. And on the top right, you have the data. And the key point of this argument here is that you can see visually which one of these models corresponds more to the data. So you can visually see, by doing simulations, you can compare simulation to data and establish a model. The other important aspect here is this is a statistical argument. You can see the distribution of galaxies or distribution of points on this plot is what matters, which means you need really large simulation to make statistical arguments. You can't just do one object. Typically, at least in this field, you need a lot of volume, which means a lot of particles, and so really challenging simulations. So that was nearly 40 years ago now, but it's still at the heart of theory. We can observe how the universe was after the Big Bang. We can observe how the universe was today, and the question is, how do we go from one to the other? How does the universe evolve? And you can ask plenty of questions that you may or may not be interested in, like what is the nature of dark matter? Is there dark energy? Are the massive neutrinos? Is the speed of light a constant of nature? Or is it evolving with time? All these kind of questions. And these are points where you can throw in, our theorist here can throw this question into her computer and try to evolve a model from the start to the present day, and then compare this to the real sky and see, whether this theory can be ruled out or should be kept for now. And so this is sort of the name of the game. And again, the statistical argument, really large volumes are needed. Now, how do we simulate the universe in the first place? As I said, we know the initial conditions. So we know how the universe sort of started because we can make deep pictures of the sky. The universe is, at least in the simulation, supposed to be infinite. So we can just use periodic boundary condition. We don't have to worry about what happens at the edge. There is no edge technically. And then we throw in the different forces we believe are necessary. So obviously we have gravity. Then you have hydrodynamics. Maybe if you get more and more brave, you can go into doing magnetic fields, radiative transfer, cosmic rays, and you can throw in more and more aspects. And then the other thing you have to worry about is what are the constituents of the universe. So you may have heard of dark energy, which is this thing that makes the whole universe expand in an accelerated way. So this we can easily absorb in a system of coordinates. Then we have dark matter, which is unknown substance that just acts via gravity. So this is also relatively easy. We make it treated as an n-body problem, we just act gravitationally. Then we have what we would call normal matter, and that's treated as an ideal compressible gas. And then you have all of the rest, which essentially everything which you can actually easily observe, which would be the stars, the black holes, dust, planets, comets, ice, whatever you want to see. This is typically treated as a subgrid model in our simulations, at least in the cosmological ones. Of course, some people may be interested in simulating individual stars and how they form, or individual black holes, and then also do simulation on different scales. But also this list here goes from easy to very hard, and it gets harder and harder the further down you go. Where does SPH come in? I think you probably have spotted already that we are doing an ideal gas, so that's where you can use SPH. Then you can also use SPH for maybe magnetic fields, for radius transfer, for cosmic ray. There's a lot of things where you can use variations on the theme of SPH to go into your physics. So this is what we want to do. This is the context, really large simulations using SPH of chunks of the universe to validate theories. There is a small example from an ongoing project from the Eagle Excel collaboration, and just showing you what this may look like. If this wants to read, it doesn't want to read. Thank you, Zoom. But yeah, what you show is just the evolution of the universe, which looks like a bit like the picture you could see on my title slide. We see some galaxies form and evolve, and how this matter just moves around. One of the important aspects is that we are doing these really large and long-running simulations, and we have this we care about the secular evolution. So we want a long baseline. And so we have to make sure our methods have very nice conservative properties. So we want to be able to conserve nicely momentum over long ranges. We want to conserve energy over long periods of time, but also angular momentum, right? You will have seen these pictures of galaxies that have these spiral arms, and so the rotation is a really important component. So we need to have a method which is really robust and conserves all of these quantities very nicely. It's not the most important aspect that we converge at the highest rates, which may be the case in other applications for SPH, but it's very important that we keep these conservation properties over really long periods of time. So let me move on. So there is no way out in this deep dive to avoid looking at a bit of the equations we want to solve, because this is at the heart of the problem. Is what is it that we actually want to do, and how can we design an HPC method that will solve them nicely and efficiently? Again, if you want to do hundreds of billions of particles, you have to think about all of the details. So the good thing is that SPH was born in astrophysics, right? In the 1970s, there's a method was implemented there. But I would argue that in the meantime, it has been now used extensively in many other fields, especially in engineering, where you can see many kinds of formulations which are really exciting, all kinds of things going from simulating ice, simulating lava, simulating snow, simulating water and oil mixture, engines, all kinds of really exciting work. And many of the developments are now of the core of the method, also in terms of the numerical aspects, on the convergence aspect, on stability of the method, on showing the consistency that everything works. A lot of the work on the SPH itself comes from this channel. This is where a lot of the inspiration comes from, and a lot of the developments. And there is a very strong community there doing this work. So maybe we can ask the question, see, there's all of this work, and this work also involves developing really nice pieces of software, nice pieces of code that are heavily used. You have an example with the dual SPH code, dual physics code, which is developed in the UK and has thousands of users that use this for the engineering applications, which is a lot more users than we have for our own software. So we could simply ask the question, could we piggyback on one of these codes for our own needs? And because they've been well tested, well developed, and everything, could we just use that for our astrophysics simulations and ride the wave, essentially, just go along and rely on what these guys have done? So let's maybe look back at the basics. Right? What is SPH? Might be maybe insulting to some of you that I have to go back to the basics, but just usually what we say is that particles are used to sample the fluid. So here the fluid is a compressible ideal gas. So it's like the simplest thing. We're just trying to solve the Euler-Boltzmann equations. We're not even trying to consider any actual viscosity, just a very simple particles used to sample the fluid. Then what we do is that particles have a spherical neighborhood with a cutoff radius h, like big H here. And we have our particles, then they will just calculate some quantities based on their neighbors, and then we'll calculate some accelerations with other particles which are within this cutoff radius h, so within what we call the neighborhood. And then once they have calculated their accelerations, which from equations we'll see in a minute, we move the particles forward in time using a leapfrogging integration. In our case, leapfrog is a choice here because it has really nice conservation property, as I highlighted before, is important for us. Now, this is very, very simple, and very often this is where things stop. So you will hear things like, this is a way to basic description, and it's also used to harness synergy, saying, oh, all SPH systems are like that, or SPH is just like molecular dynamics, which at the face of this slide, it is. You can say SPH is like, you hear things like SPH is just like Boltzmann solver. SPH is just like whatever other method you may have heard about. And, if you take a picture like this, yeah, it is. You can probably take a molecular dynamics code, make a few changes and get it to interact in an SPH way. But can you really do this when you have a trillion particle target and you want to run on the biggest computers? Can you actually deal with tweaks, or should you not think about the basics and do it, from the ground up for the really specific details of the method you care about? So let's go back and say, look at what is actually done specifically in our method. So we said particles have so we assume particles have a fixed mass. And then what we do is that we calculate the density by just summing a weighted number of particles in a closed neighborhood. So on the right here, you have just an image showing a density field where you have the dots, and tiny dots are each of the different particles. Where you have more dots, it's more dense. And so that's also the color map in the background. And then what each particle does is that it draws a certain circle, and then we define the density at that point of the particle by just being the sum, sort of the weighted sum of all of the particles in that sphere. And then, as I said, the particles loop over the neighbors to compute the quantities by a weighting function. The first one they do is the density. The other thing you can see from this plot is that not all particles have the same cutoff radius. We'll come back to this in a minute. But a typical situation in our simulation that a particle will try to find about 50 to 100 neighbors to interact with, to define it's sort of a neighborhood over which you can start calculating things. Why that number? That's enough of a number you can start taking derivatives, right? If you think about grids applications where you need a few points in each direction around your point to have a robust stencil to take a first order derivative or a second order derivative. So about the same here. You need enough points in all of your directions, even if it's more of a randomly sampled way. You need enough points that you can take sort of robust enough derivatives for your differential equations. So, right, no way out. These are the equations we want to solve. So this is the really simplest set, right? You can solve. This is just taking the simplest possible SPH method. You can find a very nice derivation of this in Daniel Price's review. And all we do here, we start from a Lagrangian, assume the particle. We have a sort of set of particles. We define how they calculate the density, and then we just follow through. The idea that if you derive this from a Lagrangian is that we have these nice properties, these nice conservation properties we like, right? We conserve momentum, we conserve angular momentum, we conserve entropy, we conserve total energy, and all of these things that we actually want because they matter over the long-term evolution of our systems. And so this is the set of equations we want to solve. It's very neat, very simple, very small, but there are already a few things we can notice from that set. The first thing to notice is that rho appears on the left-hand side on the first equation, but also on the right-hand side of the next two equations. Right? So the density, which is calculated in the first equation, enters the second and third equation. Right? What does that tell us? Well, that tells us that we cannot do this in one single loop. So I can't just have one single loop over my neighbors and then calculate my forces in one pass. I need one pass where I calculate my densities. In a second pass, I can do the rest. Right? Because then I have the rows that I can plug into my second equation. I should say in practice, you can derive a scheme where you can do it in one single loop. It gets really complicated, and especially if you think about parallelization, it becomes really horrendous. So in practice, it's not really used very much. And also for more complicated schemes, you usually have to insert a third loop to calculate extra in between quantities as well. So this is the more of a canonical approach. So this is already different, for instance, from molecular dynamics or from of the other SPH engineering applications where you have you can do things in one single pass. So you need at least two passes over the neighbors to calculate the quantities. Right? The next aspect is this. So I hinted at this in the previous picture when I defined the densities, that particles have different cutoff radii. So here's the problem. Here's just one situation. I have two particles, and this is not a crazy contrived situation. This happens all the time in all of our simulations, especially as soon as you start having density gradients. So what we have is just two particles that are close by, but they have two different search radii. The orange one, the green one. So now the question is, who is a neighbor of whom in this situation, and who is interacting with whom in this case? So, and that's a tricky question. When if you go back to the equation, you can figure out that there are actually two different regimes. So when you were calculating density, so when you're doing this first loop, orange is a neighbor of green. So the green particle sees the orange one as part of its neighborhood because it's within its circle. But orange doesn't see green as part of its circle. So we have now, sort of an asymmetric case here where one particle sees the other and not the other one. Now, in the second loop, when we calculate forces, we want to enforce some sort of symmetry, right? That's also just coming out of the formal derivation of the equation. So you can think of this as just being an application of Newton's law. If one particle gets a force from the other in one direction, the other one should also see a force in the opposite direction. Otherwise, you will have a conservation problem. So the consequence of this, in loop number 2, orange and green are neighbors of each other in sort of now in a symmetric way. So not only are we now looking at a system of equations where we have, or an implementation of SPH where we have two loops, we have two different loops. And the second one is very tricky because you're not just looking within your neighborhood. So orange is not looking for stuff within its own cutoff radius. It also potentially has to find stuff of whom that particle is a neighbor. Right? So orange has to find stuff beyond its neighborhood because it may interact with green in some nasty way. Now, how do we choose H in the first place? Right. So I said we have different variable H. So how do we actually even construct that? So it sort of makes intuitive sense that you want H to be related to density. You want a higher resolution. So H sort of is your resolution element. We want it to be related to density. So higher density regions should have a smaller search radius than lower density regions. So you can relate it in this equation that's highlighted in blue. The sort of the cutoff radius H is a function of the density, the mass over the density, and then you just have a power of the dimensionality of your problem. Now the problem you have here is that H is defined in terms of rho, and rho itself on the left-hand side is defined in terms of the cutoff radius. So you have this implicit problem that you have to solve here. So, density is itself a function of H, so we need to solve this iteratively. And, you can start screaming here because that's already a tricky problem to do. You don't want to go back to do Newton-Raphson and all these things, but that's what you have to do. And so now what you need to do is, well, Newton-Raphson or bisection scheme with loop over the neighbors at each iteration, right? Remember that the left-hand side is the left equation. The density is a loop of all of your neighbors. So you have to do a Newton-Raphson scheme, and every step you have to go back over the set of neighbors and see whether you get the right set. If not, you try again with a different estimate for your H. Right. And here you allow the second screen because you have to do loads of loop over neighbors now. And the main problem you can see with this here is that there are many things that can go wrong, especially when now we're talking about having 1 trillion particles. You don't want any of them to ever misbehave and crash your code. So you need to be really robust in your Newton-Raphson method. So you typically also have to have sort of a backup solution to bisect to get this closer to the answer in case of really pathological scenarios. So it gets quite complicated here. In practice, you can converge in 4 or 5 iterations. It's relatively fast, but it's still 4 or 5 times looping over neighbors. And it can go really bad. If you have a really bad estimate for your initial H, it can be really tricky because now you're looping over maybe 10,000 neighbors and realize, oh, that was a bad choice. And you iterate, but it's too late. You've already done your iteration over 10,000 neighbors. So here it can be very nasty. And the other problem you have is that each particle here behaves differently, right? Some particles need to do 3 iterations. Some particles need to do 5 iterations. Some particles don't need an iteration because your guess was pretty good. So here, thinking ahead, thinking of the parallelization of all of this, it's going to be very tricky because not all of them, you can't just say everybody does iteration 1, everybody does iteration 2, because some of them don't have to do this. So the load balancing, sharing the amount of work between the different particles can be quite tricky. So the calculations, and that's the last problem that's of interest. So let's go back. The deepest bit of the deep dive here is to say, what are we actually calculating? So let's take the example of the density. So again, we want this rho, which is a sum of the neighbors of m times w, where w is this kernel function, which is usually if you Google SPH and you end up on a Wikipedia page, you end up with this kernel function at the bottom here, which is sort of what it should look like. It's a bit odd at the edge, but it's a fair description of what this function looks like. And so typically W is a low order polynomial in R over H. So we calculate the distance between the particle divided by H, and then we have a polynomial function of this. So this is what we want to compute. Now, what happens in practice in a computer, right? If you already have information about particle A in hand, and you're looping over all over the B's, then all you need to compute is these 5 operations that are listed on the right. Calculate the distance, the norm of the distance vector, then you take you calculate the square of the normal distance vector, then you calculate the norm of it by taking the square root. You calculate R over H, that's 1 division, then you have the polynomial, here's probably 5 fuse multiple adds, and then the density is just a multiplication, right? So what is this, right? This is really very, very cheap. That's very few cycles. So it's very few math operations that you have to do for every pair of particle you find. And likely, this is less time than it takes to read the information of the particle from memory. Now, that may not always be true. If you are having a nicely arranged set of particles that are all aligned in memory, and you take one after the other and they all loop through, and you don't ever have to do anything strange, then maybe you're fast enough. But in practice, given everything is not arranged in a nice way, the particles are by construction completely all over the place. Some of them are neighbors of each other, some of them are not. And so you may have to skip a lot of particles when you do your loops. It's really hard for the compiler and for the computer to figure out how to efficiently fetch out stuff in memory quickly enough to do these really, really simple calculations. So that's actually a problem that is really, essentially SPH is too cheap for some of the modern computers. One comment you could make here is to say, well, okay, let's make it more complicated. You can just add more math operations and make the method more fancy. And that is true. That would be a nice way of using this spare time, where the time you wait for getting the data from memory, you could use it to calculate something more clever. The problem with that is that typically, if you do this, you actually have to read more information. So many schemes, for instance, will attempt to calculate gradients, not just the density, but maybe you also want to calculate the density gradients around you, so you can make better estimates of what is going on. Now, density gradient will have the same math operations, but now you have 3 new variables that you need to write back to, or you have to read, if you don't do a velocity gradient, then you have 9 variables, 3 x, y, z, and then they have 3 gradients in each direction. So that's now a lot more data. So you're not really improving your ratio of math to reading a lot. So let's go back to a summary of what I've mentioned are sort of the key challenges here. So, or differences from other schemes. So we need 2 loops or more of the neighbors. The particles all have a different search radius from each other. The nasty bit is we need to iteratively find a search or this cutoff radius, right? It's not set in stone at the start of a simulation. Now, in loop number 2, we need to find our neighbors, but also the particles of whom we are a neighbor. Right? So that's already a slightly different design. So we need 2 design of loops. And then each interaction is only a few flop. And the other interaction, the one that calculates the acceleration, is the same ballpark. It's not massively different in terms of the amount of calculation you have to do. Now, let's take one final thing, which is sort of also specific to astrophysics applications, is the localized time stepping. So let me walk you through this, because it's sort of unusual if you compare this to more engineering, or essentially all of the fields of science don't really use this possibility. So what I'm showing here on the right is a distribution of all of my particles in my simulation, in one of these cosmological simulation, sort of a density temperature plane. So just 2D histogram, you have the density on the x-axis, internal energy on the y-axis, or temperature on the y-axis in some astronomer-friendly units. And you can see there's a huge distribution. And you can orders of magnitude, almost 12 orders of magnitude in density, and then 6 or 7 orders of magnitude in temperature. Right? So it's a huge range. Now, if you take on the left and you focus on the blue histogram, is just the same thing, just projected on the x-axis. So again, here you have this 10 to the 11 range in density, which if you translate this to a range in smoothing lengths or in cutoff radius, it's still a factor, it's still a 10 to the 4, all right? So it's a factor of 10,000 between the search radii of different particles. Of course, particles with vastly different search radii are not neighbors of each other. They're usually in different parts of the simulation, but still you have to be able to handle such a range. The other consequence, because we're using a Coulomb condition, so you want the information to not travel more than a particle length via one time step, you have a huge range in time step between the different particles. Particles that are really, really big in low density regions or particles which are really, really dense in the high density region and can have very different temperatures, if you just calculate what is the Coulomb condition, they have vastly different time step sizes. And that's sort of the bottom x-axis of the left plot, right? You have a range of almost 10 to the 4 in time step, and our time step is in years, but this is more of astronomy units, but still the range is huge. So if you were to evolve the simulation only at the shortest time step and update every particle every step, that would be prohibitive. You couldn't run any simulation ever. It would be way too expensive. So people have done, this jump a long time ago already to only evolve the particles on the shortest time step. And that's the only way you can ever complete a simulation. Obviously, that comes with consequences on the convergence, on all of these aspects, which have been well studied, and they are well designed criteria to decide what kind of difference in time step particles can have when they are neighbors, and so on and so forth. I'm not going into this today, but this is just an additional challenge. Right? Typically, what you do is that you have this leapfrog or a velocity vert algorithm, which you can split into an operation that updates the velocities, an operation that updates the position, in this sort of what we call a drift kick, where drift updates the positions and kick updates the velocities. And what you can do formally at the level of the equations, you can split your drift into as many small pieces as you want. So you can make the slow particles, the one on long time step, have many, many, many drifts in between, so they can act as neighbors of the fast particles. And that's still entirely conservative and entirely self-consistent. And that's well-established scheme is used also for gravity and for many other applications inside the same simulations. Now, technically, this actually brings in a more implementation problem. It's a great idea, but now not only do we have all of this problem of neighbors of particles that are not necessarily neighbors of each other in a symmetric way, and all of these nasty loops, we also need to select the particles to update. Like, not all of them need to be updated every time step. So that means we need to select them, or we need to maintain lists, or we need to sort them. And so proportionally to the total stuff we do, we are now doing more logic operations than compute. Right? So we're doing more and more of this, not doing math. We're doing a lot of bookkeeping, looping through memory, finding stuff to do, and things like this. Right? And this is, this is sort of a personal comment here, but because of all of these reasons, I strongly believe it's really hard to actually get an efficient enough implementation of all of this on any of the current accelerators or GPUs, because these are not designed or not really happy when you have all of these different things happening, where you have to jump around memory, when you have to make lists, sort things, or anything. Right? If you were always running through all of the particles, they have a consistent list of neighbors and so on, that would be brilliant. But because of all of these choices we made, which are necessary choices, it gets really hard. It's not what a GPU, not what an accelerator or a Xeon Phi or whatever you want to use likes to use, right? But I may well be wrong on that. I'm still haven't yet seen an implementation that is really fully doing all of these different bits and bobs really efficiently on a GPU. So here are some implementation ideas, obviously driven from my own experience in the Swift code about how to do this. So let's first start with going back to computer science school and think about some of your algorithmic exams that you may or may not have had about neighbor finding. So here are 3 different problems, and you can choose which one you want to do in your exam sheet. But the first one is just find all of the neighbors within a fixed distance R. Problem number 2, where you get double the amount of marks, would be find the 50 closest neighbors. And problem 3, where you get 50 marks, is you get find the x closest neighbors satisfying an implicit equation to define a neighborhood. And this goes from easy to hard. Now, problem 1 is what you would need if you go back to the very first slide when I explained this very broad picture of what SPH is. Find the neighbors within a cutoff radius. This is problem 1. And that's an easy problem, or sort of there are textbook implementations for this that are really, really efficient. Problem 2 gets a bit more tricky. If you open a textbook, you find something about doing this with scaly trees and so on and so forth. Problem 3 is where we are. This is what we want to do. Right? We need to find x closest neighbors where it's not a defined number, because it will depend on its weighting function. But that's what we have to do here. So we have to solve that more complicated problem. So an easy off-the-shelf solution, for instance, from a molecular dynamic application, which has a constant cutoff radius, is not going to be good enough here for problem 3. You will have to adapt it so much that you may not be able to, you probably have better off starting from scratch rather than trying to adapt existing packages. So here's a traditional method for sort of Astro SPH. The inspiration all comes from this paper by Hermsted and Katz in '89. It's called the 3 SPH Code. And the basic idea is very sensible, right? Is to say, well, we're doing gravity, which I've also completely ignored so far, and I'm going to continue ignoring here, but we're doing self-gravity. So we have an n-body solver at the same time. N-body solvers use an octree or some kind of tree decomposition of the domain to solve for the forces very efficiently. And since we have a tree and finding neighbors, a la problem 2 from the previous slide, is using an octree is a good solution, then this is what we're going to do. We're going to use the octree to find my neighbors by looping around and walking around the tree and following pointers and all of these things. And that's not a bad choice, makes sense. This is what you would do. It's easy. Since you already have a gravity code, this is really, you know, the right thing to do. It's easy, it's robust, it's fairly easy to do in parallel, because you can just have each particle is completely independent of the other. They can find the neighbors in their way. And many codes use this. So if you, the gadget family of code, the gasoline family of code, the phantom code, all of them use this, and many other codes that make use of this method. Now, you know, this works very, very well, as I said. One maybe challenge here is that this is not really what, you know, modern computers like to do, right? Because here you're talking each particle independently. Each particle now has to walk the tree in a slightly different way, because maybe they have to go up one more level than the particle next to it, or they have to jump in a different area of memory. So each particle is completely independent, but which means you can't really put them in a vector instruction and say, I'm going to do 15 or 16 particles at the same time, or 1,000 particles at the same time on my GPU, because each of them has to take a slightly different path in the tree. That's not very good. And the other, you know, so that's, you know, that's a problem, because they all do something different. And the other problem is, of course, that jumping through memory is really bad for the kind of prefetching idea. So that since the compiler doesn't know where you're going to go next, because you can't know what the structure of the tree is at compile time, compiler cannot say, oh, I'm going to need these particles in a few milliseconds. Please send them from RAM ahead of time. There's no way you can predict this. So that's also a problem here. So if we really want to get some efficiency, we need probably to think about this in a different way. So the way we do this in Swift code is to say, let's go back to problem 1. Right? Problem 1 is the easy problem. It's the one where I just have a uniform grid, where I set my grid size to be sort of the size of my cutoff radius. And so my cell size naturally matches particle the neighbor search radius, right? So if I now take a look at the blue particle in my green cell here, and I design my cutoff radius is the red circle, I know that by construction, all of my particles are either in the green cell or in the orange cell. Right? So at the point where I'm done constructing the tree, I have defined the entire geometry of the problem. There is nothing left. There's no tree walk to be done. I know just from geometry arguments where to look for my neighbors. So that green cell, so that particle only has to loop over the other bodies in the green cell. So none here because I'm lazy at drawing, but you know, the other particles in the green cell and any of the other ones in the orange one. So that's very simple. You can just write this as a couple of for loops, right? And if you do this, so looking at sort of a C code version of this, you can just write it as a loop of all of the cells, the first loop, you know, millions of cells, loop of all of the 20 cell neighbors in 3D, then you get the gathered counts of the particles, and then you have a double for loop over the particles, and then they do their interaction. That's very simple. This is now a quadruple for loop. Everything is very predictive, right? The compiler knows, okay, I'm going to loop over this. This is going to happen. I need to fetch my particles. It's very organized. There's no jumping around in memory. This is much, much cleaner. It's much, much better. And you can think ahead of how you're going to do this. If you're going to do this by hand, you could imagine that you could take 2 cells and ask the compiler or do it by hand to use vector instructions within the 2 cells. Right? The 2 cells will have about 50 to 100 particles each. So that's nice. That's a small amount of memory, fits well in cache. You can run vector instructions there. Then you can do the rest. You can use threads. You can use MPI to do all of the other loop at the top. So you could, in principle, just put a pragma OpenMP in front there and live happily and have a semi-decent, you know, parallelization here. There's one thing that this doesn't take into account, is that if you put a pragma OpenMP or some sort of very basic parallelization, is that remember that second nasty loop, the one where some particles have to do some extra iterations, where you have to go back for some of the particles to redo 1 iteration, redo 2 iterations, redo 3 iterations. So if you just distribute this over the different CPUs, that's not going to go well, because maybe you have one CPU somewhere that has some particles that we need to redo something. So it sounds like you need something a bit more dynamic than just a plain distribution, right? So let's keep this idea in mind and talk about parallelism here. So go back to the mesh that I had. So one thing that we need to think, you can think about is to say, well, if I have this grid with my particles, the cell pairs do not need to be processed in any defined order. All I care about is by the end of my time step, I have done all of the pairs, right? So whether I do the orange top-bottom interaction here, or the green left-to-right interaction, first, it doesn't matter as long as I've done all of them by the end. So what I can do is I can make a long, long list of all of the pairs of cells and a long list of all of the self interactions like the one in pink, and then just have the different threads come in and pick up some work and do something. What's the advantage here is that the cells can have vastly different workloads just by construction, right? There may be some higher density regions, some lower density regions. So if I have a very, very long list, that should even out. If one thread takes twice as long to just do one pair, that's fine. The other threads just do two pairs, and that the system will adapt. So we need some sort of runtime dynamic scheduling. It seems like the natural solution to this problem. This is where task-based parallelism comes in, which is a mechanism to sort of distribute the work across threads in a sort of an efficient way by just having a list of operations and a dependency saying you can do this before you can do that, and have a mechanism to distribute these tasks to the different CPUs. And each thread picks up a task which has no dependencies or no conflicts and just computes it. When it's done, it goes back and says, I'm done, just pick the next operation. In terms of SPH, this is also nice because you can express your problem very nicely in terms of just the different tasks, different operations that chained, and they have to happen in a given order. So first you have to move the particles, and you have to do the density, which is our loop 1. Then we have this correction loop, which in Swift we call the ghost iteration. And then we have the loop number 2, which is the force, the acceleration, and you have the time integration. And so you can express your physics very nicely in this graph as well, which is very nice. You can see what the code is actually doing. You can sort of move things around if you want to add more physics. If you want to add more physics, it gets a lot more complicated. You have a more complicated graph. Here's one where you also throw in some gravity calculation and some interaction with stars. So there's a lot more going on. So maybe you feel like screaming again, but this allows you to visualize what is going on and also tells you what the code is doing in what order. Things can happen if there are no horizontal links. Things can happen at the same time. You can do the gravity, for instance, at the same time as the hydrodynamics, which is an advantage. You don't have to wait until all of the cells have done all of the nasty loops. If you can start doing gravity, you can do it at the same time if some threads are idle, which is what happens in this result plot. What I'm showing here is what we call a task plot in our case. We have on the x-axis the workload times you waiting in front of your computer. Y-axis is different threads doing different thread IDs, and in different colors is what they're doing. And at each point in time, each thread does something different. Right? Some of them are doing hydrodynamics, so like the density loop, the loop 1. Some of them are doing loop 2. Some of them are doing time integration. Doesn't matter. They just pick whatever is available in the thread in the list of tasks. And the interesting point is that they all end up at exactly the same time. So here you have almost perfect load balancing. There's no time wasted where a CPU does nothing. You have achieved your goal of the perfect parallelism here. The other interesting aspect is these sort of aquamarine greenish tasks in the middle, which are these long bars. These are the ones where we have to redo these nasty iterations, right? You can see they are quite long. They take a longer time than the other tiny, tiny bars. But it's not a problem because we can do something else at the same time. So you have some nasty particles. Some of them have to do a lot more iterations, but it doesn't matter because the other threads can just do something else. And so this dynamic scheduling is our solution to this problem of having this dynamic problem, essentially, of iterative problem. Let's go a tiny bit deeper, because one thing I haven't said is that we have this uniform grid, and you can think of, well, that's a problem because we have this large range in density, so that's surely the stupid solution, and indeed it would be. So what you can do is when you have this pair interaction, then you have a lot of particles, which means you're in a high density regions. What you can do is you can recursively split these cells into smaller pieces, and then only compute the interactions that are needed. And you can do this only if the cell size keeps going below the cutoff radius. And what you can do, you can keep doing this until the cell size is smaller than the size of an L1 cache or an L2 cache, depending on your architecture. Which means that when when the task comes in and says, I'm going to do this operation on this pair, the data it has fits nicely in a really small cache of your CPU, and you never have to go back to the RAM until the very end when you write back. So that allows you to really compactify and have this really fine-grained tasking approach by just splitting, making this sort of AMR, sort of adaptive mesh and recursive scheme where you need it to. And maybe one final aspect on this pair interaction, this is like, if we are in a deep dive, we are now Mariana Trench type of deep dive level. So this is like the deepest of the deepest you can go, is to think about how can we now speed up the interaction between two cells that are touching. Right? So we need to have all of the particles in cell A at the top interact with all of the particles in cell B at the top. So the naive way of doing this is just to have a double for loop going all over the particles. That's sort of an n-square problem. But that's super easy to write, super easy to vectorize. Your compiler will do a magnificent job for you, but it's also very, very slow because you're actually doing a lot of useless operations. So one thing you can do is you can project all of the particles on the axis that links the cells, sort them, and then you can only walk along that axis. So if you look at the bottom panel, you take the particle in red, it doesn't need to go all the way to the end of the cell. As soon as it has walked on the axis a distance of the cutoff radius, there's no need to go further than that. So you don't need to do the whole n squared. You can stop there because you're done. And that's it. You can only interact with these particles that are potentially, they're not all neighbors, of course, because they could be at a long distance along the y-axis, but this is a better list of candidates. And this is especially the case in 3D. If you think about it in 3D, you take two cubes that just touch by a corner, then the number of particles that actually interact is very, very small. So you gain enormous factors by trying to do this more cleverly along the axis, right? But now this more clever approach is also tricky because now you're doing, projecting particles on a line, and you're doing some sorting action, you're looping in an unconventional way. So again, this is tricky, right? This is not something that the vectorizer or a GPU will happily go along with unless you do some hard work to get it to do it. So, but here this more clever approach beats the n-square version by orders of magnitude in real life applications. So let me maybe just finish with a few comments on this local time stepping and how the problems it also brings, and sort of an HPC in an HPC context. So one thing you often like to plot to see how good your code is parallel efficiency. So you take a fixed problem size, and you run it on one core, and you run it on 2 cores, on 4 cores, and so on, and you see how much faster it is. If you run it on 10 cores, it should be 10 times faster. What I prefer to do is revert the axis and not plot it as a gain factor, but as the actual raw time, right? So here we have a number of threads on the x-axis and a time to solution on the y-axis. So more threads should go faster. If you have a perfect code, it should be along the dash diagonal. So if you have a fixed time, right? This is what you would get for perfect code. If I now run Swift on a representative problem with a fixed time step where I update all of the particles every single time, I get quite a nice evolution here. It's nice parallel efficiency. It's not perfect, but it's pretty good. It's also a complicated problem here with a lot of high density contrast and so on. What I can do instead is to say, well, okay, I'm going to do my other approach where I only update the fraction of the particles that actually need updating based on my time step criterion. But what I'm going to do instead, I'm going to drift all of the other ones. So I'm going to move them so they can act as neighbors. So this is now much faster. So if you look at the y-axis, the curve has dropped a lot, right? We're spending a lot less time to get to the solution, but the efficiency is a lot worse, right? So we flatten out much more quickly. So in terms of what your HPC application will look like, people will be like, oh, but your code is not very efficient. Yeah, but it's a lot faster. You can keep going and say, well, actually, I don't need to move all of the particles. I only need to move the ones that are neighbors of the guys that are active. And how do you do this? Well, you first have to do a preliminary tree walk where you activate the tasks only in the region of interest, and then you follow this by the actual calculation. So again, that sounds like a lot of nasty work, right? But it's beneficial. That's now the purple curve at the really bottom, where you only really do the only tiny amount of work that actually needs doing. You don't do everything, right? And so it is faster, but it scales worse, right? Putting in some numbers here, going from the really naive scheme where you do everything every step to the better scheme, the fast scheme, it's 100 times faster, but the efficiency is getting terrible. And so if you plot this parallel efficiency, people will say, oh, but your code is not very good, right? It doesn't scale. Yes, but it's a lot faster than a method that scales. So scaling is not the only thing that matters here. Why does it not scale? Well, if you look at the bottom, the numbers on the curve are the numbers of particles updated here, every step by on average, right? So at the end here, you end up with fewer particles than you have threads. So that's becoming really, really tricky because you have so little work to do. How you're going to efficiently distribute it is really a complicated problem. So, and it gets even worse on the multi-node aspects. So how about multi-nodes? So I mentioned this task-based business before. You can do the same thing. You can do the communications. You can send and receive data as part of tasks. So if there is a pair of cells that overlap between two different MPI domains, I can do an MPI send and an MPI receive as part of a task. And when the data has arrived, then I can say that to the local task scheduler, okay, this is ready. Now you can do the task that needs that data. And before the data has arrived, the scheduler is like, okay, I can't do this. I'm just going to do some other purely local work, right? That's very easy. It also means that since it is all handled by the tasking system, whoever is implementing physics in the code doesn't have to worry about MPI because it's all handled in the background. You also don't have to worry about threading or atomic or mutex or any complicated concept. It's all handled by the scheduler, which is one of the nice things as well of task-based parallelism. It all happens in the background. You don't, as an application scientist, you don't have to worry about parallelism, which is something nice. Just to show that it actually works, here's a set of task plots now showing 8 different nodes and showing that they're all doing very nice work in parallel, but they all also end finishing almost all in think. And this is showing that this whole method works. Smallest time step problem. Clearly, it's impossible to distribute n particles on m nodes if n is smaller than m. Right? And that happens all the time in our big simulations. You have maybe, you have 10,000 MPI ranks and 5 particles to update. What are you going to do? Right? You can't distribute, you can't split the particles. So the solution really is that we have to make these steps as cheap as possible and cut all of the overheads. And the main overhead is MPI communication. So we really have to cut that. Now, how do you cut MPI communication? Is to say, I don't want any MPI communication on the really small steps that involve a few particles. So how do you do this? Well, you put these particles at the center of your domains. And you could imagine growing your domains organically around these particles and make sure that only when you have large steps with a lot of particles active, then you actually have to go over the MPI boundaries to do this work. So in an astronomy way, you could do this by first identifying the galaxies, which is where the particles are. Then you can grow the domains around that, and bam, you have an efficient code. Now, any cosmology numericist in the room will know that identifying the galaxies in these simulations is a really tricky problem. So we're not going to do this. Instead, what you can do is construct to construct a global task graph of all of the calculations in the simulations. Remember, we have this graph telling us what task is to be done before which one. So we do this for the entire calculation. And we can build this as a graph for the data nodes and the task that hyper edges. And then we can add extra costs for the communication tasks. We say, oh, these tasks are really expensive, so that we try them to minimize the number of them. And then it becomes a standard graph decomposition problem. And there are like plenty of open source solutions to this. So in practice here, we use the Metis library, which will just split our graph evenly such that we get the same amount of work on each node. And also we make sure that we have as little fast particles, or as little of these super active regions close to the edge as possible. And finally, to show that it works, this is a Swift weak scaling test. This is on a Cosma 8 system. Again, this is a weak scaling, so I'm taking the same problem and making it bigger and bigger and bigger until I reach the edge of the computer. So if I make the system, the problem 8 times bigger, I use 8 times more CPUs. And so here I'm using the entirety of the system. Disappointingly, I made a mistake in the Slurm submission script. So the last point is off the curve. I'm waiting for the job to go back into the queue, but it's not easy to get access to the full system. But bear with me, it should go down and behave like the other points. And so that demonstrates that basically we can achieve extremely nice weak scaling of our simulations on one of the largest systems we have access to, which is what we want. Ultimately, if we get a bigger computer, we want to make a bigger simulation. Remember, this is this whole statistic argument that we want to make really large simulation of a really large chunk of universe. So we need to make, if I get a bigger computer, I'm not going to make my simulation run faster. I'm just going to make a bigger simulation because I can. And so that's exactly this approach here when I do some weak scaling. The last point is interesting. This is 500 billion particles, so it's satisfying our goal of going as big as possible. And the other point you can try to make here is to look at the second y-axis on the right-hand side. This is the time it takes to update one particle on one core. So that means doing 3 loops with 80 neighbors each and doing all of the interactions and all of the findings and all of the activation of the task and everything. And so we take about 10 microseconds per particle, which translates as about 40 nanoseconds per particle-particle interaction on average. So this is the performance. This is sort of a raw performance, and you can see whether other implementations can achieve the same if you want, to go to an accelerator or a GPU or whatever on another machine. This shows you how small, how fast this can go, at least on purely CPU implementation. So I'll finish here. Hopefully, the second movie will show, and it will not show. So I will end up here. This was supposed to be another extract from a cosmological simulation, showing you some shock fronts and some nice images. You'll have to ask me later if you want to see it, but that's where I end. So maybe just a few conclusion points. The specifics of the astrophysics SPH are such that it's not easy to just take off the shelf other pre-existing implementations. There are some specific needs related to the multi-time stepping, the fact that particles have different smoothing lengths, the particles need to do these extra iterations, and also the fact that these iterations, the calculations are really, really cheap, means that they are not necessarily well suited to modern computers, and also not really necessarily well suited to where the exascale trend is going, which is sort of a problem we have to face. And I think I'll stop here, and I'm happy to take any questions or comments, or if you think I'm all wrong about GPUs, I'm also very happy to hear about that. Thank you very much.
In terms of questions and answers, it might take a moment for them to come through. So I'll just wait for the questions to come in. I think Ben Rogers has something that's, I assume he's just typing now. From a personal perspective, I'd just like to thank you for the talk as well. So I thought it was really good to see. So I think, as somebody who comes at this often from an engineering angle, the scale of what gets talked about with sort of the astrophysics community, simulations using SPH still blows my mind.
Yeah, it's a different regime, right? I don't think one is they're both sort of labeled as SPH, but to some extent they are fairly different, right? When you're talking about doing some really nice engineering application, we have maybe tens of millions of particles, but you're doing a fifth order time integration with the third order converging SPH scheme, which is doing some nice viscosity term and interaction with boundaries. There's a lot. This is very, very different from our very cheap-ish SPH method running on much larger systems and having different needs. But so it's a really wide range of applications.
Yeah, absolutely. Okay, so I've got two questions in the Q&A. So the first I'll read verbatim. So it's from Ben Rogers. So you use the density summation, which gives an implicit problem requiring the multiple loops. With variable smoothing length in engineering SPH, we use the continuity equation, which avoids this issue and avoids the really complex loops and extra computational complexity. Why is this not used in astrophysics codes?
Yeah, that's a good question. I think mostly tradition. There are some implementations that of sort of a more, I think people have gone from what I showed here to sort of the full extreme of going to a full ALE scheme with Riemann solvers and everything, where the density is indeed exchanged between particle as a quantity. There's no real in-between work where you would not do the full ALE approach, but actually solve the continuity equation. So I don't really have a good answer to that. I think it's just tradition and ease of implementation. Although it's, by the look of it, it's actually not that easy in the end. For technical reasons, for writing the equations down on a piece of paper, it's very easy and robust. But it's definitely not a satisfactory answer. But I think that's unfortunately the real answer.
So perhaps an example of where two sort of topics can converge on.
Yeah, I think there's still a lot to learn. As I mentioned, there's a lot to learn from the engineering development, right? They have been pushing the method a lot more than really we have in terms of getting the convergence, getting the method to behave better. Whereas probably we have gone the other way and saying, well, instead of making the method better, if I just throw more particles at the same problem, I'll still get a decent answer.
Okay, thank you. So an anonymous question. What type of computing architecture would you like to see? I suppose that's in the context of the SPH problem that you described today.
Well, I think from what we have seen, and it's also the case in our sort of Excalibur type of experimenting, the main problem we see is really moving stuff around in memory. Or whether that is within a given node or between nodes or everything, it's just that we are limited by that. So anything that can help with this, making some type of accelerator that is able to reshuffle information in RAM without bothering the CPU may be interesting. I think one thing that sounds interesting, but we haven't tried and don't know if it will be successful, is like this type of Bluefield type architecture where you have the ability of having a separate chip that does the MPI communication for you, at least in theory, and can in principle also be used to reshuffle your memory. That can possibly be an interesting way forward. You could imagine, for instance, that you could reserve your main CPU, which has all of the fancy vector instruction to do the math. Then you have next to this an ARM chip or sort of a set of ARM chips that move the stuff in memory such that you only, I mentioned we have to do this selecting the particles that are active or sorting the particles, all of this. This doesn't require a fancy CPU. It just requires fast access to shuffling the RAM. So, you could maybe dream up a machine where you have an ARM chip that does this reshuffling, and then next to it, you have the CPU that does only the math operation, right? Which is sort of also what people do when they have a GPU. They have the GPU that does all of the heavy lifting math operation, and then all of the stuff which is too complicated for the GPU, they let to the CPU to do, and then they ship it over. So maybe something like that would be something that would be interesting to explore. It doesn't exist, of course, but if you're asking me to dream up an architecture, that's what I would like to get for Christmas.
Okay, so perhaps if NVIDIA carry on buying ARM, then we might see something like that in the future. Yeah, so there's one more question come in from Ben Rogers again. So we are at the limit of our session here, but if you've got a moment, then I'll ask.
I'm here the whole afternoon.
So Ben noticed in the load balancing plots, there were gray patches labeled as sort. What is this and why is it needed? Is this to optimize cache access? So this perhaps goes back to what you were just saying, in fact, about the memory reorganization.
So I showed when I said we're going the deepest of the deepest bit, when I'm mentioning this moving, the particles along the axis of the two pair of the cells. So when you do this, you first project all of the particles on the axis, and then you want to sort them along that axis, such that you can then walk along the axis to only use the most likely candidates for your neighbor search. So what we have done, instead of having the sort operation done within sort of the pair task, we have outsourced this and labeled it separately. So we do the sort, and then when the sort has been done, then we can do the actual pair operation, which is just using the result of that sorting list. So this pseudo-variate list is sort of outsourced. The advantage of that is, well, first, where the time is spent. And the other thing is that if you sort, you can also get some extra buffer. So you don't have to sort exactly, as long as you put some extra delta. So you can reuse your sorted lists for multiple time steps. You don't have to do it every step, as long as you add for some extra buffers here and there. So that means you can that allows you to run the pair task, the actual neighbor finding operation independently multiple times before you have to redo another sort. So that's why it's also nicer to have it outsourced as its own single standalone operation.
Okay, thank you. So we have one more. So Tom DeVoist has asked, does your efficiency depend on having large differences in density and time steps across the domain, or would it also work when differences are less? So for example, 1 to 2 orders of magnitude.
You mean when I showed the speed of plot by using the smaller time step? I think that's what you mean.
Yes, I think so. Yeah.
Right.
Yeah.
Well, sort of no, by construction, because if the simulation is a lot more uniform, then all of the particles will end up on fairly similar time step sizes, because if they all have the sort of same density and sort of the same temperature, then the distribution in time steps become a lot smaller. And as a consequence, the gains from only doing that bit of work is becoming minimal. So then you pay the costs of this extra logic over just brute forcing the problem and saying, oh, I don't care, I'm just going to do all of it, right? If all particles are active all the time steps, then don't be clever. Don't try to be clever, just brute force the problem. It's a bit the same with same consideration between grid codes, where are you doing something with an AMR solution where you refine, or versus a grid code? If the region where you have to refine is most of the box, then, well, you may as well not try to be clever and just brute force the calculation by doing a uniform grid everywhere.
Okay, thank you. So no more questions have come in, and we are past our time. So I think we'll probably draw to a close there.